Okay, so in a previous lecture, I asked the class if anyone had learned about something called Newton's method in Calculus 1, and a sufficient number of people said that they didn't, so that I think what I want to do is take a step back and teach you Newton's method because I do think it's important for you to know, especially since there's so many computer science majors in here. And even chemistry majors might benefit from knowing this when doing optimization problems. So Newton's method is something that a lot of instructors will kind of gloss over in Calculus 1. And I think one of the reasons why it's glossed over is that most math professors in the past, I think, were kind of more focused um, on maybe the non-numerical topics in calculus. And by that I mean that math professors, they like proving things, they like long integrals, uh, they kind of tend to like these types of topics. And not every math professor likes to compute things that are tedious to do by hand, right? But myself, as a mathematician, but also as a data scientist, I know that computing things with a computer can be easy if you know how the algorithm works, right? And that's what Newton's method is. Newton's method is an algorithm that is used to solve the following problem. Um, uh, so maybe so. What's the problem? So given function f of x, find the zeros of f of x. I we want we want all the values for x for which that's holds. Not all, but we want like one value for where the function is zero. So um, for example, if we have some function like this, then these values here, maybe I'll call this like C1 and C2, those would be the zeros of that function. There might be more over here, but here are two zeros of the function f. Okay. Now, finding zeros of functions is incredibly important and related to many different things. I might assign like a writing assignment to kind of describe the things that you can do with finding zeros. But for this lecture, I'm just going to focus on telling you how to find these zeros, or how to find approximations to these zeros using an iterative algorithm. Okay. And for those of you concerned that this might not be too much a part of Calculus 2, the immediate lecture after this on differential equations is going to introduce a method that's similar in its construction. So this is related. Okay, so we're going to start um, with a function that looks like this. I need to draw this bigger to illustrate how each of the pieces work. So okay, I think that's big enough. So this is your function f, and we see that there's a 0 right there, okay? And we don't know what that 0 is. We have no idea what that number is, okay? And we don't even know what the graph of the function looks like theoretically, but with the picture we do. So what information can we use about the function to find out this value? Well, how about this? Let's make x0, let's take a guess. So x0 is just guess at for a solution. Okay, let's make sure you can read that. Okay, so you make a guess, right? And as soon as you make a guess, you have an immediate output from that guess. F of x0, x0, right? And what do we have access to when designing this method? So we have f of x for all x. Right, so for any x that we guess, we can plug into the function. But then we also are going to allow ourselves to have f prime of x for all x. So we can look at the derivative's value for any x that we choose. So this was our first guess. How can we use the first guess to make a new guess? And the hint is that we can use the derivative somehow. Well,
would we say like set up the derivative equal to 0?
That would tell you when you're at like an extrema in a little cusp, right? That will tell you the critical numbers of the function. Like critical number be there and there, and we're looking for the zeros.
Oh, okay, okay.
But no, you have to take guesses before you'll figure it out. So what's the slope of this line? What's the slope of that red line? All of you should know this based off of the first homework assignment. What's the slope of that line? It's not like a number per se, but you can tell me what the slope of that line is.
The slope of the line is the derivative.
The derivative of the function evaluated at
x of 0.
Right. So this line here has slope equal to f prime of x naught. Now, looking at the picture, isn't this intercept right here a better guess at the 0 than our first guess? Do you see that? There's the 0 we want, and we originally guessed right there. Isn't that a better guess? Aren't we getting closer to where we want to go?
Yes, sir.
So let's figure out how to find that new guess and call it x1. Well, this is easy, right? This is a line passing through that point and that point with that slope. So we know the equation of a line, right? It's what is it? y1 minus y naught is equal to the slope times x1 minus x naught, right? That's the equation of a line passing through those points with that slope. Okay. Now, what do we know? The only thing so we know that and that, right? So y1, so the y value here is going to be 0, right? So y1 value is 0 because that's where we're at, we're on the x-axis. Do we know the first y? Yes, the first y is just f evaluated at x naught. Do we know the slope? We do, right? The slope is just f prime evaluated at x naught. And now x1 is what we're trying to find. And then x naught, we know that we took a guess at it, but we know that. The only thing that we don't know in this equation is x1, so then we solve for x1. So if you divide both sides by the derivative, and then you add x naught to both sides, you get that x1 is equal to x naught minus f of x naught over f prime of x naught. So we didn't know that, but we picked a number to put in there. We picked one. Once we pick that, then we can subtract off f at that number divided by the derivative at that number, and we get our new x1. Okay. But now, let's do the same thing again. Now, we immediately get an output, f of x1. And then, if we look at the tangent line, shown in blue, this has slope need to make more room. This has slope f prime at x1 is the slope of the blue line. But now look where it intersects right there. Let's call that new number x2. Isn't that a much better guess to the actual 0 of the function? Like, even on your screens, you can see like, that's basically the 0 of that function. Right?
Yes, sir.
So how do we find that x2? Well, it's the same thing that we did here over again. So it would just be x2 is equal to the previous guess, which is x1, minus f at x1 divided by f prime at x1. So, and then we could do the same thing again. We could keep on going. So then the general formula is that x n plus 1 is equal to xn minus f at xn over f prime at xn. This is Newton's method. It's an iterative method for finding the zeros of a function. Okay. So in the trig example that we looked at yesterday, the inverse trig example, at the very end of one of the problems, it asked us to find the points of concavity of a function. And in the textbook, it solved it via Newton's method. Well, concavity happens when the second derivative is equal to 0. When we solved for the second derivative, we had a function. And then if we apply Newton's method to that function, we will find the zeros of that function, which told us when the second derivative was 0. So it's a useful technique when you can't solve explicitly for a value, but you can approximate it using Newton's method. Now, Newton's method is not always guaranteed to converge. There are functions like maybe like the cubic function where this is not going to work, but a lot of times it will work, and it will work fast. So let's kind of illustrate how this can be used in an interesting way. So here's a problem. Approximate square root of 2. Now, square root of 2 is like pi. It's an irrational number. Irrational numbers have an infinite non-repeating decimal approximation. And computers have a finite amount of memory and storage. So computers cannot store the true irrational numbers like pi or square root of 2 or square root of 3 or e. The computers cannot store them. They can only approximate these numbers, right? And that's because of the infinite decimal expansion with no repeating, infinite decimal expansion, there's no pattern, is how could you store that, right? So how could a computer store that? It can't. It has to approximate it. So how would you approximate that, right? Like if you were to come up with some way to do it, well, one way is to say, oh, wait a minute, maybe if I'm clever, I can say, so I can say let f of x equal to x squared minus 2. What are the zeros of this function? What are the zeros of this function? Values for x for which that's equal to 0. Somebody speak up.
Positive or negative square root of 2.
Right. If you plug in square root of 2 here, you square it and then subtract 2, you get 0. So the zeros are x equals plus or minus square root of 2. So once we know that the zeros are precisely root 2, then we can say, well, maybe we can run Newton's method on that function to try to find one of the zeros, which will give us an approximate value to the square root of 2. So, and you can see that it's going to work out graphically pretty nice. It's just the parabola taken down by 2, 1, 2. So this would be root 2, and this would be negative root 2. So if we just make a guess over here somewhere is our initial guess and then run Newton's method, hopefully we'll run into that. So I know that, for example, 4 is bigger than root 2. So I'm going to make a guess of 4. I know 3 is bigger than root 2, but I just guessed 4. Okay. So, all right, we guessed 4, and now we need to do Newton's method. Now, typically I would never do this by hand. I would write a program in Python or Julia or something to just compute this quickly for me. By a show of hands, or just say yes or no in the chat. Say yes if you'd like me to show you how I would do this using Python. Say no if you'd like me to do it by hand.
Is it possible to say yes and no?
It looks like there's enough yeses that I'll do it with Python, but as I'm doing it, I'll write notes like I would be writing on the board.
Thank you.
Okay. Okay, so this is the thing we're going to implement on that function with that first guess. And I'm going to be using Jupyter Notebooks, which are kind of like the standard data science way to interact with Python. So real quick, let me open it up. Spider is one of Spider is more of like a scientific computing IDE. So Spider is this one right here. That's if I'm going to do like real like heavier things. So when I'm just exploring a concept, I'll use Jupyter Lab or Jupyter Notebooks. I'm just going to use a notebook for now. And then let me just go to a good directory, maybe teaching. I'll just make one in here and make a folder later. So I'm going to go new, Python. Okay, so I'm going to import a few libraries. And again, if you've never seen Python coding before, I encourage you, even if you're not computer science majors, I encourage you to look Python up, or look up, yeah, Python would probably be the best first language. And teach yourself on YouTube. It's gonna come into, it's a very valuable skill to have, basically. Okay, so I'm importing a plotting module. So this is kind of the standard plotting module, matplotlib.pyplot, and I'm importing this. This thing that I'm importing it as PLT, so I can access all of the functionality of this module by calling this. And you'll see me do that here in a moment. And I think that's all I'm going to need, actually. So I'm going to go ahead and import that. And now, let me make this a little bit bigger so you can see. Okay, so now I'm going to define my function. So there's a few ways to do that, but I'm going to do it this way. So I'm going to say fx. Okay, and then I'm going to return x squared. So this means squared when you put the double asterisk here. X squared minus 2. Okay, and so what's the derivative? We're going to need the derivative of this function. What's the derivative of f?
2x.
It's what?
The
2x.
derivative of what?
The derivative of the function that we're looking at. It's just going to be
2x.
Yeah, 2 times x, right? Oh, I need to give it a name. Maybe I'll call this function df of x. And then we're going to return 2 times x. Okay, so those seem to be like the main functions that we'll need. Now, I can say maybe, I don't want to import any modules, so I'm going to make a domain list as, say maybe x for x in range 0 to maybe 5 or something. This, all I'm doing is I'm making a domain. So this is just, I'll show you what this looks like. It just looks like this. And I could do this using a module named NumPy, but I don't want to import anything else because this is already new for many of you to see Python. So once I have a domain, then I can do a plot. I can just say plt.plot. So I give it the domain first, so domain, and then I need to make the range, which will be f of x for x in domain. Hopefully that makes sense. It's kind of jaggedy, but you see, like, here's the x-axis at 0, and it's going this way. So root 2 is like right over here somewhere. Okay, so let's go ahead and start making our points. So we said that x naught was equal to maybe 4.0. Okay, so that means that x1 would be equal to x naught minus f at x naught divided by df of x naught. Okay, so we can go ahead and do that. So let's see what happened with our points. So I'm gonna make this is like probably the worst plot I've ever made in Python. So I apologize for those who know Python. I'm just trying to keep it very simple right now. So I'm gonna plot that, and then I'm gonna put points over it. So actually, let me, what does x1 look like? It's 2 points. Okay, so now to put points, you use the scatter method. And I'm going to say the first list is going to be 4 points. I can just write it out the way it should be, x naught, comma, x1. And then, so that's my domain for this scatter of points. And then my range will be f of x naught, comma, f of x1. So I want to see where the points are going. Or, yeah. Actually, no, I'm going to show you the points separately. So just put these in lists like that. And then, okay, so there's my first scatter. And I'll say color this like, or maybe I'll make the markers nice and maybe like crosses for the points. And then the first one I'll color red. And then maybe the next one, now I'm gonna put x1 in there instead. And then maybe I'll color this one green or something. So you see how we're moving the function down, right? Like our first guess was here and we were there. Our next guess was like right over here and there. So now let's go ahead and make our new guesses. So let's say x2 is equal to x1 minus f of x1 divided by df of x1. And let's go ahead and do this again. I'm not writing any loops because I wanted to keep it like I would be writing on the board. But for those of you that know computer science, you know that you would probably write a for loop to do this for you. So now x2 divided by df of x2. So now we have a whole list of points. So what is x2? What is x3? I think we're already getting close to the square root of 2. If anyone has a calculator, you can verify. But yeah, let's look at what the points are doing. So I'm gonna just do this over again. And now I'm just gonna color them all red. So in order to do that in one go, to color them all red, I can just do all at one time. So x1, x2, x3, and then f of x1, f of x2, f of x3. So see how they're starting to jumble up down here? That's because we're getting close to the 0, right? Actually, let me look up something real fast. Matplotlib library, grid. I want to show the grid. So for anything in Python, there's typically going to be lots of documentation. That's one thing that makes Python so nice, is that there is a lot of documentation. There's lots of examples. I see that this one has a grid layout, so I'm gonna click on that. How did they make that grid? That's all data stuff, dot grid true, maybe? Let me see if this works. I'm just gonna copy that. Do plt.grid true, maybe? Perfect. Okay, so there's the x-axis, and we're like right on it. So if we go one more time, I bet you we're gonna be like close. So we'll say that x4 is equal to x3 minus f of x3 divided by df of x3. Okay. There it goes. All right, so now we're just gonna do the same thing. Now I'm just gonna throw in that x4, throw in x4, f of x4, and then also with these functions, you can always, with the commas, you can stack them according to the entries, and that's kind of like a nicer way to do it. Okay. But those are all contained in that one function, all of these properties: domain, range, marker, color. All right, so let's look now. Yep, x1, so x1 gave us that, x2 gave us that, x3, x4. We actually are getting a little bit further down there. Maybe one more time, I guess. I'll do this all in one go. Paste that, and then up here I'll say x5 is equal to x4 minus f of x4 divided by df of x4. And then I'll put x5 in here and see what happens. Yeah, they're just like jumbled up now. It's not even moving. So, okay, well, what's happening numerically? So, I'm gonna say copy that, paste. So I'll call this capital X. I'll call it capital X. So now I'm just gonna make a nice little print statement. So for I comma little x in enumerate. So enumerate just, it gives me an I together with the x inside of big X. So it gives me 0 and then x0, 1 and the next 1, 2 and the next 2. And I'm just going to print. So you can print strings. This is just a technical thing. If you don't program, don't pay too much attention to it. It's just a way to make a nice little plot. So x, I could just, yeah, so maybe I'll do like I guess equals x. Close out that f string, print like a little space. So we started at 4, 2. Oh, that's annoying. Let me just. Yes, make it look better. So this looks to be approximate solution. And if you check with your calculators or you Google square root of 2, this will do it for you. This will be probably a better approximation than you'll get. All right. So I'm going to go ahead and stop this recording. Okay. And then we'll pick up another recording in a minute or two.